So we saw different types of motions like linear, translatory motion, rotational motion. Now all these things, whatever we saw was for a particle, correct? Now what we are looking at is a rigid body. Okay, see, a rigid body, like how we can define a rigid body is a body which does not deform under any other external forces. Okay, so that's basically it's a rigid body, like whatever we see. Okay, it could be like it could be a table, it could be a chair, it could be a lot of things. See, these are all rigid bodies. Okay, now there are two types of motions a rigid body can undergo. So first one is translation and rotational motion, correct? Now for a rigid body there are two equilibriums what you guys have to know. One is a translatory equilibrium and another one is a rotational equilibrium. Okay, now whenever we talk about translational equilibrium, so here the forces acting on the body, the sum of all of them should be zero. Meaning, see, translatory equilibrium, correct, or translational equilibrium, the body can undergo rotation motion, but it should not undergo translatory motion. Okay, so something like this. The second one is rotational equilibrium. See, in rotational equilibrium, the external torque acting on the body, sum of all of it should be zero, or sigma tau is equal to 0. Here the body can undergo translatory motion but no rotational motion. See, something like this. Okay, see, simple example for this is, see, a fan. Fan is rotating, correct? Is there any translatory motion? No, I'm talking about a ceiling fan. Okay, so ceiling fan, it undergoes only rotational motion, no translatory motion, correct? So there is translatory equilibrium. Okay, so different types of examples can be given for these things. Okay, now to solve the problems based on this equilibrium, we have something called as free body diagram. Okay, now free body diagram plays a very important part, because let's say you have some particular object standing on, let's say there is a ladder standing on a wall. Okay, like it's resting along the wall. So here, where is the center of mass? And if the object is moving, let's say it moves for some time and then it stops again. Now where is the center of mass? See, here the position of the center of mass will change. Now how do we get to know? It's based on the free body diagram. Okay, see, one simple example, look at this. We have an object, so it's on a frictionless plane, and then see, we have a pulley, and then we have a weight. See, the weight is actually it's pulling the object down, correct? So how many forces will act on the particular body? So to figure out how many forces act on the body, we use free body diagram. Okay, see, look at this. These are all the forces which act on the body. See, we have frictional force, and then we have weight, we have normal, all these things are there, correct? So this is how we represent a free body diagram. Okay, now whenever we talk about free body diagram, we have to figure out, okay, these forces are there. Since the body is in equilibrium, the summation of all these forces is 0. Like, see, weight and normal are in opposite directions, right? So if you're taking weight to be positive, then normal will be negative. Or if you're taking normal to be positive, then weight will be negative. So there are certain sign conventions which you guys have to know. So in the next video, you will see how to solve a problem based on free body diagram.